Recording started. Claudio.
Good afternoon, everyone. It's my pleasure to join your kind invitation to present the PhilLab activities. My name is Claudio Jacopino. I'm the head of the PhilLab Explore Office. That is the part of the PhilLab where we explore, as the name says, various way we can apply innovative technologies in the Earth observation domain. Specifically AI, but certainly not all AI, as we presented the last time. We're looking at various different other technologies. Today, we will look at more details at some of our internal research, thanks to the help of our fellow, that basically these are our postdoc, that spent a few years with us at the PhilLab, and they have, in fact, they have the capabilities and the time to really delve in some specific topics, as well as then supporting all the rest of the lab activities. Today, so this is really just a sample of some of the activity. Last time, I gave you a very large overview. That's where these projects really just are a piece of a much bigger puzzle. But I mean, today we have the opportunity to really see the stand of them, and each of them is really a great piece of work. So today we have Gilberto Gorace, that is the first speaker. He will talk about hydrology, as you can see already from the title. He's in fact involved with data from IGGM and MAGIC. And I will not say more. This is all for Gilberto. Then we will have Gabriel, that instead is our biomass expert. And therefore his talk will be about the using of biomass. This, I'll say, is about the bias quantification on biomass that it does through various means, including the data of our ESA biomass mission. And then we have Ricardo. Ricardo instead is going to, his talk is more on agentic AI and the use of socioeconomic data for various applications, including agriculture and health. And last speaker will be Roberto Del Prete, that instead is a research focus on onboard AI and SAR, that I'm sure you're going to find quite interesting given your expression of interest from last time. In fact, I try to, in fact, collect the research that is more close to the your expression of interest for last time. So please, I'll leave the floor to Gilberto for the first talk. And obviously, you can ask question. I think the way we have arranged it is that at the end of each presentation, we'll give just a few minutes for questions, and then we move on. All right.
Okay.
Please start, Gilberto.
Thank you, Claudio, for your introduction, and thank you all for being here in this webinar. So, as Claudio previously said, I am Gilberto Gorace. I'm a research fellow, and I work on hydrology. Especially, my work revolves around the use of AI for the NGGM and MAGIC missions. Then, sorry, I cannot move my. Okay, so basically, the NGGM and MAGIC missions are is a constellation. Okay, so terrestrial water storage. Sorry, I wasn't. The slides were not moving. So terrestrial water storage is a very important variable to monitor the global water cycle because it is the only, let's say, indicator of the change in water on a global scale. At present time, we have data for this given by GRACE and GRACE follow-on missions, but those data has a limited spatial and temporal resolution. With this new constellation, this new ESA-NASA constellation of MAGIC, basically we will be able to increase the precision and reduce the latency of these terrestrial water storage products, especially going from a monthly frequency to a sub-weekly frequency. The goal of my research is to super resolve the resolution of these products and increase the spatial resolution typically from 3 degrees to 1 degree. This means that, for example, 3 degree correspond to a 300 kilometer wide patch, which is of course very, very coarse to do analysis on local scale. So basically, this is the workflow of the approach. So we start from a coarse input, which is at 3 degrees. We plug in some auxiliary data that in our case come from ERA 5 or other climatological datasets. And then through an AI model, we obtain this downscaled output at the target resolution. And an example is given in this image here, where you can see a snapshot of the Amazon region. On the left side, you see the original product from NGGM, from the satellite, and on the right, you see the downscaled product after the application of the algorithm. What we used is a set of climatological variables from ERA 5 that kind of want to take into account all the phenomena that happens and that are related with the hydrological processes. And we also use a digital elevation model for topographic information regarding the case studies. Of course, they come at very higher resolution because ERA 5 is 0.1 degrees. So we perform an aggregation both in time and space to go back to let's say, our desired target resolution. And another important thing in this pipeline is that the terrestrial water storage is a variable with a certain memory. This means that the changes in water do not only depend from, for example, the precipitation at the present time, but also for how much it rained or the temperature of the previous months. This is why we consider a 3-month delay of each dynamic variable in order to consider also the slow processes that affect the total water storage. This leads us to a total of 212 input channels. So the network is quite, let's say, quite large. Here you can see a snapshot for Africa of each input variable, and excluding, of course, the time. The temporal information is given as a cosine of day or year and sine of day or year. And here are all the inputs that we are currently using. So the approach that we selected is a so-called high-to-high approach, which means that we train the AI model to predict a high-resolution map. Then this map is upsampled back to the coarse resolution of the satellite and then compared with the satellite product. The negative aspect of this approach is that the model can also not learn the relations between the inputs and target at the high resolution scale, because in the loss function, there is no constraint at the target resolution, but only the constraint at the coarse resolution with the satellite. The model is a very simple unit neural network composed of an encoder and a decoder, as you might know already, where we reduce the dimensionality of the image, increasing the number of the feature in the encoder, and then in the decoder we go back to the original size of the images, reducing the number of feature up to 1, which is our only output channel, which is the downscaled terrestrial water storage. So this is the pipeline. So we have the high resolution inputs from ERA 5 to a model to predict a high resolution output that then gets upsampled back to 3 degrees, so the resolution of the satellite. We compare it with the native satellite product given by some simulation environment. Then we compute the loss function, and then with backpropagation we update the weights of the model. This is a GIF about like the learning process. So as you can see on the left, the reference here is never seen. So this is an unsupervised learning approach, which is the closer to reality, because in reality we won't have a ground truth for reference. We have a ground truth here because we are using a simulated framework of these products, because of course the missions are not launched already, so we work with simulated data. And so we have a reference which is given by the ESA Earth System model, but we don't use it in the training. We only use it for comparison and validation after we finished the downscaling process. We selected 5 regions of interest based on the relevance of the hydrological signal, so Europe, Africa, Amazon, the Ganges, and the Mississippi, and we trained a separate model for each region. Here, for example, you can see a snapshot of a downscaled map for Africa. And so we have a ground truth at 3 degrees, of course, from the model, and we have on the right the satellite product. As you can see, we have 3 different mission scenarios, so GRACE continuity, NGGM, and MAGIC. MAGIC is basically GRACE and NGGM combined. And as you can see, the quality of the satellite product increased a lot from GRACE to MAGIC. And this also reflects in the downscaled product, because as you can see, the quality of the downscaled GRACE Sea-like is much worse than the one from NGGM and MAGIC. Then we upscale the downscaled product back to the original resolution to compare it with the satellite, and as you can see, they look pretty much the same, because of course the model is trained in a supervised manner on the satellite product. Now, if we compare the results from the different products, we can see that, for example, some amplitudes are correctly reconstructed, looking, for example, in Madagascar, and other one in the south eastern part of the map, or here this blue patch around the Congo basin. This is the same for Amazon, and the same concepts apply here. So you can see the improvement in the quality between the GRACE, NGGM, and MAGIC product. We can conduct an investigation on the trends, meaning how the terrestrial water storage evolves in time. And here also you can see the difference from going to GRACE Sea-like to NGGM and then to MAGIC at both the native and the downscaled resolution. So to wrap it up, we want to downscale the simulated data from 3 degrees to 1 using AI. And we are using 5 daily level 3 data from end-to-end simulations, using also auxiliary data from ERA5 and the DEM. Then what we can assess from a global analysis of the results is that we have a very high temporal correlation with the ground truth for all the mission scenarios, with Pearson R greater than 0.75. And we don't lose structural coherence at the core scale. This is very important because it means that whatever happens at 1 degree, still we have the certainty that at 3 degrees we are producing a product that is of the same quality as the original satellite. But at the same time, of course, we are able to reconstruct some high-resolution structures at the target resolution. And finally, there is a very a noticeable improvement from GRACE Sea to NGGM and MAGIC at the downscaled level, and this is due to the much better quality of the satellite products. As you can see here on the right, on the last column of the table, you see the improvement from using GRACE to using MAGIC. And for example, in the variance ratio, that is how the model is able to reconstruct variability of the reference field, we have an improvement of 47%, which is huge, as well as an increase in all the other metrics, and a reduction in the mean average, in the mean absolute error for the trend. So this approach, of course, has many limitations, mostly because the pixel-wise metrics are not reliable to assess a method. Because, for example, if you retrieve a structure, a river, let's say, for instance, and the river is slightly misaligned with respect to the ground truth, a pixel weight metric will be very, very, let's say, penalized. So it's very difficult to globally evaluate the performance of the unit. And of course, we don't have any constraint at the target resolution. So the approach is kind of purely data driven. So future developments are currently testing the approach on different products and do some hyperparameter tuning and an improvement on the loss function, considering also physics-based terms. And what is going on now is also the identification of hydrological extreme events using the downscaled product to see if this approach is able to has also an application, let's say an applicative utility for the hydrological community. And thank you for your attention, and I'm open for questions. Okay, so I think that, Gabriel, you are next, right?
Yes, thank you.
Okay, so I think you can share
Yeah,
your screen.
Exactly. Let me just figure it out. This should be the main one.
I see a question from the chat, Gilberto.
Yeah. Felix is asking some questions.
Thank you, Felix, for your question. So at present time, there is no hydrological model that is used. For example, water gap or list flood. We are not using an hydrological model directly in this framework. However, the simulated product are produced from the ESA system model, which has basically with the 2.0 version, that is the old one, it is driven by ERA interim and the land surface discharge model, hydrological model, that is a very old one. But now we are using the ESA system model 3.0, which is driven by ERA 5 and list flood. So the hydrological model is not included in this pipeline, but it is included, let's say, in how the simulated data is produced.
All right. I think that if there are no other questions, I can introduce my presentation as well. Well, first of all, thank you, Gilberto, of course, for your talk, and also Claudio for the introduction. Thank you also for the biomass expert. I don't think myself as one, but still, thank you very much. The idea of this talk then is to talk a bit about how we can improve models that already exist using machine learning. All right. So you can think of this as a way of correcting errors and biases that are present in some data sets, either if they are based on machine learning or inversion model, but how we can approach to them. And more than that, I think I would like also to introduce some of the ideas that we construct when we are trying to approach a problem in the machine learning area. I guess I'm having the same problem. There we go. Well, after this introduction, some topics here that I would like to talk to you about it. First, of course, I want to pin out why do we estimate above ground biomass and what is above ground biomass. The role of the CCI data set, which is a very important one that was mostly developed at ESA, how biomass is estimated and what are the orange of data that we are using here. The EBA dataset, which we use mostly as ground truth for our analysis, some main limitations of the model that we are using, and also I'm going to talk how important they are to help us to understand our results. How do we model systematic bias? So this is the main result of our approach, and of course, limits of extrapolation and the shifting domain that we might find in this kind of analysis. The idea here is not to talk exclusively about biomass, but also how do we approach our problem and construct the conclusions given the results that we have. Well, first of all, then, why do we estimate biomass? Well, estimating biomass, especially at a global scale, it's essential for climate reasons because it tells us a lot about the ecosystem that we are analyzing. Most of the above ground biomass that we have are in fact stored in forests. So to study biomass is also to study forests, of course. Uh, well, some facts about the distribution of forests in the world. Basically, they account for 56% of the terrestrial organic carbon. The biomass specifically from trees, it's about 75% of the living biomass that we have. We are also made out of biomass, but this is not what we are trying to measure, actually. The biomass on Earth in general, 80% is stored in forests, and the carbon content for each kilogram of biomass, it's around 40 to 50%. So depending on the tree species and the ecosystem, this proportion will vary, of course, but this is more or less what we are trying to estimate. Basically, to estimate biomass is to estimate the amount of carbon that we have in the forest. And this is especially important because the forests, they play kind of a double role. They're not only storing carbon, but also they take away carbon from the atmosphere in general, which means that when we are trying to map the amount of the biomass that we have, we are not only talking about how much is found in there, but what is the potential of taking away carbon from the atmosphere, from this this balanced net of carbon that we have. And there is a lot of uncertainty in this estimative, especially in areas where we have more biomass. So for instance, at a global scale, we have the CCI data set. It's for the Climate Change Initiative. And basically what we have from the results nowadays is that exactly in the tropics areas where we have more biomass is also where we have more uncertainty as well. This means that we are not exactly sure how much biomass we have in there. There's this range of uncertainty, of standard deviation, if you want. So every time we want to access the changes in biomass, for instance, from one year to the other, we have to consider that there's some changes that they might be just by chance, just by as a result of the limitations of the model, especially the CCI. CCI works well at a global scale because on average, the errors and the biases, they cancel each other. But if we are going to use this data in a more regional scale, then we have to improve the accuracy of this data, but also the bias of this data, specifically the ones that are associated with certain mechanisms that are very specific from the forests. The way that we do that first is that we have to try to find some ground truth, right? So something that we trust more than the estimative. I mean, everything is an estimation. There are errors in everything, but nowadays we use generally LiDAR as one of the best ground truths that we have to estimate biomass. But we also have to take into account that the estimation of biomass doesn't depend only on the size of the tree, but also of their characteristics. I mean, depending on the wood density, the diameter, at the breast height, they're all important. But what we are actually most of the time estimating from a remote sensing point of view is the tree height. The other characteristics, we try to understand from the environment. So is this a tropical forest? Is this a rainforest? What are the most likely species that we can find in there? So we can estimate and also take a guess on what are the other properties that will lead me to estimate biomass. Okay. Well, in this case here, the ground truth that we are using are those around 901 overflights that we have from the EBA dataset, and they're translated for 125,000 samples at the pixel level. Of course, that this estimation from the LiDAR perspective to the pixel level that is going to be used as a ground truth itself has some limitations, then errors and uncertainty that will be translated into our ground truth. But we have to try to take that into account as well. So what we do here is to compare the results from the ABA data set to the results of the CCI and try to understand where one thrives and the other one doesn't, and also if there are errors and bias that are common to both data sets, so we can have a better clue of what we are trying to model in this instance. So basically, this is what I just said. First, we compare to characterize the bias, and then we use the airborne laser scan data set to calibrate the CCI AGB. Well, then we can talk a bit about the results that we have from the bias analysis. Basically, we can see that the estimation that comes from the EBA dataset itself, of course, is better than the CCI in this instance because it was designed for the Amazon region. So we can expect that, of course. But also, if we analyze only the distribution of the errors in both data sets, what we have is that the CCI, there's a trend, a tendency to overestimate the amount of biomass, even though we have a saturation at some point in between 300 to 400 megagrams per hectare, as you can see in this scatter plot here, the first one in the middle. What we are trying to do is to reduce this effect of saturation. Saturation mainly affects CCI because of the data sources that we have to estimate the tree height and the density of the canopy. What happens is that in some regions of the Amazon, we have so much biomass that the signal never reaches the ground. So at some level of the tree height, we can't tell if this is actually the ground or if it is the limit of penetration of the radiation that we are trying to retrieve the signal, right? The idea here is that just to show you that although the EBA data set, which is the scatter plot on the right side and the distribution in orange, looks good enough, right? We have errors that are centered around zero. The structure of the bias actually happens in both data sets kind of equally. So for instance here, this is just to show how the standard deviation and the variance of the errors are completely different from both data sets. But even so, we have in the structure of biases here, they repeat itself not on the same level, but in the same structure, right? In the first line, when we compare the signed errors of the data set, we can see that there is more variance to the errors from the CCI, depending on how much biomass you are estimating. But if you do the logarithmic representation of those signed errors values, what we have is that the structure is the same, although in different scales. So because of this, we have enough evidence to try to model this structure of bias that we can see here that is not random. And that's the idea. If something is not random, that means that we can model it and eventually reduce the influence of that in the CCI data set. How do we do that? We are working with a very simple model, which is the random forest, although it is very good for a lot of tasks. Even it can work for classification, but also for regression. The idea of the random forest is to produce slightly different decision trees that will compete against each other to see to give you a prediction. And The idea is that one single tree that you are comparing the values of the estimative of that tree will have a higher variance. But if you average different trees, then you have a lower variance and a more stable prediction over time, depending on how much you train and how many times you split your trees to give you more and more specific data. Of course, there is the limitation of overfitting, and depending on the regime that we are trying to work with, it might not work because we have different things that are happening based on the same variable. But we can list some pros and cons from them, from the model that we are using, right? So different from some models that we saw previous, there is no need to scale the variables in the random forest because they work independently. Works really well with nonlinear data as well, and this is something that we saw before. The errors are nonlinear in the CCA dataset. Works with different data types, and considering that we are going to use here some classification information from ecoregions as well to give us an insight of the structure of the forest. This is a good thing to work with. It is very robust to the difference in variance that we have in different those beams of biomass, this different range of biomass. We have a different variance of the errors, and it handles well high dimensions of data. So the more features I have, the more complicated it is to take into account all of them. And they're also robust to multicollinearity, which is how the variables that are going to be used for the model, they relate to each other. The bias, the cons of this model is that it tends to bias the estimation towards the mean of the variable that we are going to use. The predictions, because we are talking about decision trees, they tend to be not smooth, right? Which means that it will identify breaks in which after that break or before the break, we are going to have an estimative. And this will create some breaks in the estimative that we are trying to do, especially if we are working with regression and not with classification. Also, if there's a lot of noise in the data, it can overfit, and it's very domain specific, which means that if there are two different drivers of the target variable and they work in such a way in one area that is not the same way in other area, then the model might not be able to identify that. And this is actually something that we see here. This is just comparing the strategy, is a ablation study here in which we compare the strategy of the sampling of the information that we are going to use to train our model. So depending on the limitation, the radius of information from in between my train and my test data set, I can see that the performance is reduced, but also the capacity to extrapolate the information is improved. So the idea here is to have a consistent result, a consistent error across different estimatives of above ground biomass. And this is what we are trying to achieve here. So although the R square, the coefficient of determination, is decreasing as far away we take the train and the test information to compare to each other, we can see that the power of explaining the correlation, the variation of one variable given all the others ones is decreasing, but also the capacity to extrapolate is actually increasing. This is just one idea, an example of the limitation that we have with the random forest, and there's ways to approach that. If you can see on the right of the predictions that we have after random forest, we can see some breaks, some artifacts that are they seem to not be related with the biomass estimative itself. We see those as stripes, and they are caused because we use it as features latitude and longitude as well. So we can either take out those variables, but then we are going to miss the spatial context of the variable, or we can substitute by other means of giving some kind of hint of where something is located, but that doesn't rely on such a strong break either in latitude or longitude. Because if you think about longitude doesn't change in the y-axis, and latitude doesn't change in the horizontal axis when you're trying to create those breaks. So there are better ways to do that. Here's just a practical result of what happens when we have a larger distance between the train and the test samples that we're going to use it. Basically, we have more smooth results because then we are taking out the influence of spatial autocorrelation from the variables. So we are limiting the capacity of the model to understand and overfit space in our model, even though it's not clear that this overfitting was affecting the results in the numbers, in the distribution. We can't see that. We have to look into the result and consider the limitations that we expect from our models. Here is a result after the calibration. Of course, as I just said, from the 0.5 kilometers distance to the 20 kilometers distance of the sampling, we don't have a very clear difference, but if we look into the map, we can see that we actually have better results in the 20 kilometer sampling strategy, although the numbers, the R square and the RMSE, they're a little bit smaller, but I would trust more the model that is based on the 20 kilometer sampling, for instance. So the idea of the results that we have in here and how we interpreted them, it's to understand, I hope that you learn it, that we can use the comparison of different models and results to understand the nature of our problem or to trim down what are the hypotheses that we have. The model choice, of course, it comes also with a limitation choice. So we have to be aware of what is the limitation of our model. Otherwise, we won't be able to interpret the results. Same, just an example as well of how important the sampling strategy was for the model, and the indicators that I'm saying, the metrics that we have, the R squared, the RMSE, individually, they only tell a part of the story, of course, in a sense that we have to understand the context of the variable that we are trying to model and also the context of the results after we model something, of course. And the idea is that to work with machine learning, and this is something that we can take into account through all the presentations that we're going to work here. The idea is that we have to not only know the data and the models, but also the problem itself. If we consider just one of them, we're going to limit the possibilities of interpretations of our results, right? And also, just to close the presentation, I always like to keep in mind this message from Robert Coase, which is that if you torture the data long enough, then the data will confess to you anything. And the idea is that using data and metrics, it's not very productive if you don't look into the results itself with a very critical mind, and also not trusting just one single metric to compare everything, every outcome, without relying on the actual interpretation of the results, given what you know about the nature of that. All right. That would be all. Thank you. And if you have any questions, I'd be happy to help you.
Armando has a question. You are muted.
Okay, thank you. I was waiting. Thank you. Gabriel, thanks for the presentation. It is really cool to see that you already have an above ground biomass map from biomass. It's already all Amazon. It's really cool. I was not expecting so early. But question is about, so is this a level 3 done with backscattering? So how did you obtain the original map before the machine learning adjustment?
Just to be clear, this is based on the CCI data set and not the biomass satellite. Okay.
All right.
So this is why we start from this baseline, which is the CCI. The biomass data set, we are doing some experimentations with this data, but it's going to be mostly for the upcoming foundation model that we are developing here, right? So until here, we don't have any results from the biomass satellite. Okay, now we are testing some of the tools that are available on Snap and how we can translate that into our model as well. So there's a lot of trial and error, which are not in this presentation at all. Sorry if there were expectations about that data set, but we are not ready to present results yet.
No, it's totally fine. So you repeat all the time CCI too. So it's totally fine. I just confused it. That's all right. So did you to apply this model when then the biomass product arrives?
Yes, I mean with the we have the hypothesis that the biomass product estimation from the level 2 and level 3 will be way less affected by saturation mostly. So by using that, we can enhance the performance of our model specifically in these areas here from 300 to 400 megagrams and above. So the idea is that the biomass will help us to estimate that. And it will be most welcome as well, also because the CCI works with 100-meter spatial resolution, while the biomass would be at a 250 resolution.
Perfect. Thank you.
Oh, thank you.
I think if you don't have questions, we can move on to the third presentation, because we don't have time.
Okay, thank you, everyone.
Yes.
Can go for the next.
All right, so I'll share my screen. You guys can see my screen, right? All right, so I'm going to talk about some applications, especially using some socioeconomic data and trying to measure phenomena on the ground that relate more to the economy in general. I think it's not moving. Okay. So we started from this and we looked at what are the anthropic factors that actually can cause a degradation of nature and what are actually the risks that derive from those factors. So this is a framework that already exists in literature. And so on top of this framework, we analyze what are, like possible applications in terms, like especially using microeconomic and macroeconomic data. And we looked at how satellite data is used for those applications. And basically, we wanted to understand where are the gaps. And I mean, I'm not going to go through all of them, but for example, we saw that looking at insurances and drought insurance, most of the applications use a very coarse spatial resolution because, like especially if you look at drought finance, those applications focus on larger areas. So there is some potential for some sensors that are not really developed in these applications. And the same is true, for example, we looked at health and especially on dengue, where like most of those applications use very coarse temporal resolution data. So, for example, monthly data, whereas this disease is a disease that evolves frequently. So there's really the potential there to exploit some weekly resolution data. So after this mapping, well, we actually started working on top of some previous work where I leveraged geostationary data to produce basically, NDVI maps at the very end. So some vegetation status data set. And the potential there is, even though this data set has coarse spatial resolution compared to the usual MODIS or other fine resolution datasets, it can, the potential of the improve temporal resolution is that by taking multiple observations per day, you can remove much better the effect of clouds. So this has been tested in the past in some research, especially looking at some case studies for drought monitoring. I have used this data set also. So after producing this data for the Horn of Africa region, I've used this data set to basically do a forecasting based on a diffusion model. So in this model, I take different conditional variables, which basically represent the physical conditions. So like derived from ERA5, so like the moisture, temperature, and so on, and other variables. And conditional on those, the diffusion model is basically able to produce a forecast of what's going to be happening in the future, in the next days or months. And well, the nice thing of the diffusion model is that it's basically, given its probabilistic approach, you can also model uncertainty and see how and also we found that it's actually very resilient to extreme conditions. So especially in the case of heat and drought, like the model was able to deliver much more accurate forecast compared to other deterministic models. Also, I'm using a similar data set actually derived from MTG, which is like the more recent sensor compared to Seviri. And actually, I'm using data derived from the sensor, same data. So again, NDVI maps. I'm fusing it basically with MODIS imagery, doing a double diffusion model to do a super resolution. And at the end of this pipeline, basically, I want to get to the resolution of sensor. As I was talking before, we also have looked at diseases, and especially on dengue. And what I have, actually, we started from what you see on the right-hand side is like a risk measure of dengue in the whole world. It has been previously produced from in some literature. And I'm using this to, and this is based actually on a two-step model, which takes into account in the first part some economic factors, travel distance to the nearest hospital, quality in general of the health facilities, and so on. And then in the second stage, you have like kind of a mosquito model. So basically to take into account surveillance factor from the first stage, but also what are the conditions that can actually make the mosquito survive and reproduce. And starting like taking the data from that risk variable actually changed a bit because they assumed kind of a linear relationship between the variables, and I used this generative additive model, which is nice because it helps untangle the marginal effect of the variables on the risk of dengue, basically. And here, well, you see the variables are standardized, so even though, I mean, for example, in DVI, it doesn't really make sense. The numbers you see on the x-axis. You can see how the marginal effect of the variable on the output. For example, you can see in the population, as the population grows, of course, you have an exponential increase in the risk of dengue disease. And then I'm also using this variable as a baseline for a model to predict dengue incidence rate. So dengue incidence rates are defined as the total number of cases over 100,000 population. So here you see basically I have rasterized some administrative data into a map for Brazil, Peru, and Colombia. And basically, those are the variables I'm using. I'm also using some night lights. So this is basically a proxy for human presence, because I mean, you know that mosquito presence is not the only factor that is important for the spread of the disease. Of course, you need like the human presence in the model in order to predict the future cases that are going to happen in 1 week. And I mean, yeah, this is the model I first showed you in the previous slides, so to model the probability of them basically. And those are the variables I'm using instead in the prediction model in the second, in the last slide. I'm also working on some applications in agentic AI, especially through some ESA projects. You might have seen that we have fine-tuned a model called Eve. So this model has been fine-tuned on Mistral with some Earth observation text data. So data that is really relevant to our domain. And what we are trying with the team here at the PhilLab is trying to leverage this data to leverage this model to evaluating its performance in agentic pipelines. So you might know that nowadays, you know, like all those LLMs have agency features. So basically, they are able to interact with the environment, and they make decisions, and be autonomous in their operations. And especially, I'm trying to apply them in the context of drought insurance. So basically, in a setting of a multi-agent system, you have like an orchestrator and different specialized agents, and at the end, one agent is able basically to produce an estimate of a price insurance. And this type, the objective is to benchmark how good the whole pipeline is in terms of efficiency, but also in the final output. This is sort of the pipeline that we have. Like we have this, we call it agentic ecosystem. Basically, we have a front end, but also we have in the back end, we are connecting to different MCP servers where we can gather data from different sources. And it's nice because we can interact with different databases belonging to the EO domain in general. And especially here, you can see, for example, we have been working with the EO dashboard, which is a dashboard where there's data and narratives from ESA, NASA, and JAXA. So basically, we have designed few agents that are able to retrieve stories from this dashboard, and also they are basically able to interact with those stories, retrieve additional data, go to databases, and in the future now we are working also on integrating an MCP server from Google Earth Engine, so we can go and retrieve additional data. Also, we are looking at possible other MCP servers for other missions. So what is nice is that this general context, we are able to interact with different platforms and ask queries. And on top of this, we have Eve, which is a model specialized on Earth observation data, and is better compared to commercial models in doing all those. And this is how it looks, the EO dashboard. And here we have a very dummy example of the dashboard of what we have produced, the front end, so where we are able to interact with Eve and able to retrieve information and ask queries. And yeah, that's it from my side. So if you have questions, I'll take them.
Thanks, Ricardo, for a very nice and different presentation. Do you have any questions from the audience? Okay, if not, we can just move on to the last presentation. Thank you very much, Ricardo, again.
Okay, I think it's my turn.
Yes, very good. Thank you, Roberto.
Okay. Okay, you should be able to see the presentation. Right?
Yes.
Okay, first I would like to say hi to Professor Armando Marino. I remember to have read his papers when I was a PhD student about polarimetric ship detection. The topic that we discussed today is about AGI for space, so how to bring on-orbit deep learning algorithms to solve specific classes of problems directly on the sensor, directly on the satellite. But first, 2 words about me. I'm an internal research fellow at FIAP, and I work on model compression, quantization, and edge computing pipelines for on-orbit execution. You can think of me also like a sort of dietologist for deep learning models, because we don't want AI models to melt when we deploy them on board CubeSats. So we really need to shrink them at the most to maximize their efficiency. Well, we know that the AI in general, the geospatial sector make a lot of use of AI. There are many applications, ranging from environmental monitoring to health, urban planning, logistics, and so on. And the question could be like, why we need to process on orbit while we already do this on the ground and it's already efficient. But to answer these questions, maybe it's better to take a step back and to analyze what is the traditional data handling chain that is commonly used by almost all the satellite. You have in general an Earth observation satellite that acquires a certain product over an area, the so-called level 0 product, which comes not calibrated with many artifacts, if you want. Then this product gets downlinked to a ground station. Assume there is availability of a line of sight to a certain ground station. The final product gets stored into a data archive center. And finally, we process this product, we correct for this artifact, we calibrate it, we correct also the geometrical errors that might be arise during the acquisition. And finally, this product gets released to the end user. Now you can understand that between the acquisition and delivery of this level 1 data or level 1B or level 2, there can be some delays, even on several hours. And this is not something that you might want to have, specifically in time-sensitive application. Think about a flood or a wildfire. You might want to have the information as soon as you can. So that is mainly why, one of the reasons that we try to push this concept of onboard deep learning, onboard AI, if you want. The second reason concerns the limited bandwidth. Of course, you can create more ground stations, but this is expensive. So since we are creating more and more satellites, and since these have this novel advanced sensor that produce larger and larger volume of data, this sooner or later it can become a bottleneck. One of the way of solving this bottleneck is this smart data handling on orbit. So you downlink only what you need or specific areas, or you downlink only the relevant actionable information. And of course, like I said before, the other problems is concerned to the latency. So in every case that you have a time-sensitive application, like a wildfire, a flood, or the detection of specific targets like vessels, you might want to deliver that information to the coastal guards, for instance, as soon as you can, so that you can have a rapid intervention. And there is a whole new vertical segment specialized on this kind of application that deploys small CubeSat 6U in general, directly assessing one of these tasks, like Aurora Tech that was mostly focused with wildfires. Now we have also FISA2. We had Canini, where I had the chance to work in Australia last year. But we have many satellites coming up every year. One of the tasks that in which we worked in the lab is the task of vessel detection. Like I said, having the time critical information as soon as you can is mainly beneficial for having a rapid response. The thing that we developed here in this study in particular was how to use directly the raw level data, so the level 0. So we made a study, and this is published, on how to detect vessel from raw Sentinel-2 data. So we directly take the IS information, which is an information which is carried out by a transponder mounted on board these vessels. And we use that to correlate to the Sentinel-2 images. We created the first 2 data sets of raw uncalibrated Sentinel-2 data. And we verified that our algorithms can run on board an hardware which is very, very closely to the one that is on real CubeSats, with execution below 26 seconds per scene and consuming less than 2 watt of consumption. Another study, okay, this is one of the inference that you might want to see in the paper. This is how we detect the vessel in the raw level 0 data of Sentinel-2. Another study that we made is how to translate the same concept to the synthetic aperture radar. So how to analyze directly raw synthetic aperture radar for vessel detection. The problem gets more complicated because, as you can imagine, raw SAR data it's a bit more different from optical imagery. It needs a specialized processing to get to the so-called SLC, which is the focusing. But we're going to analyze this furthermore in this presentation. What we demonstrate in this study is that you can use the phase for revealing where are the vessels in level 0 data, because the vessel acts like a specific strong scatter in a cluttered area, and this creates a specific pattern inside the phase. This specific that you can see in this top image. And we use a specific technique also to shrink the model to a very small size to detect these vessels and have a large throughput. One of the problems, like I mentioned, is that when you have models that needs to be deployed on orbit, you have also a problem of computational efficiency. You might not want to have the largest model on orbit if they can be very heavy. Let's say even if they are very, very accurate, you don't want to have models that are very slow. You might want to consider having models that are like less heavier and accept to lose 2-3% in performance if you can gain faster speed. And to do, let's say, this model shrinking, there are many, many approaches. In literature, you will find approaches like quantization that reduces the bit depth of your model, or pruning that directly deletes some part of your model. Let's put it in this way. Another way is to knowledge distillation, so to transfer knowledge from a teacher, a big model, to a student, a smaller model. And finally, the neural architecture search. One in which I was very, very interested was the neural architecture search. And I think that is potentially still untapped because it can be combined to the other models, to the other techniques that you've seen before. And the study we made inside the lab is how to use this, how to create a framework on neural architecture search, and how to create very, very small models that can be deployed on orbit. What we did was create this framework, which can be decomposed in several different sections. Imagine that you have a model generators that randomly create several different architectures. You have several different blocks that gets constructed one after each other. And this constitutes a single architecture. Then you have an optimizer that profiles each one of your models on board the edge device that you are trying to target. So you have a specific satellite that mounts a specific hardware. You see how fast this model runs on that hardware and how accurate they are. And this optimization is carried out in a loop that tries to brutally, let's say, optimize the topology of this architecture until you find an optimized model. What we demonstrate in the paper that is published, and I can send you the link maybe after we can take this offline, is that the model we create with thanks to this framework are 3 times faster to the models of literature, like MobileNet or ResNets, but they achieve the same level of accuracy. The bubble size indicates how many parameters these models they possess. And we can see that they have like few thousands of parameters compared to multi-million parameters from literature. In a classical deployment scenario like this, you can see how they segment burnt area. And in particular, we target two different devices, Jetson Orin and a MyriadX, how they perform compared to the traditional models from literature and how they compare against the ground truth. We applied the same technique to another task, which is the vessel segmentation from another dataset. And these results have been presented in a conference. You will find them online. Also, the framework, if you want to have a look and play with this software, is available to this link. It's online on GitHub. I give you some seconds so that you can scan and get access to the software. Okay. Another task which we are working is the deployment of a geospatial foundation model on orbit. So how we can take very, very large models and make them available for on-orbit execution. It's a very challenging task, as you can imagine, because usually geospatial foundation models are very large models and they don't fit the requirements of a CubeSat. Specifically, the project that we are developing is called HydraNet, and it's concerned more on how we can orchestrate the different downstream tasks. So you have multiple heads, like one head for building regression, one head for road segmentation, one head for flood mapping, and so on and so on, and how we can make a very smart head handling and activate only the relevant head to a certain downstream task. Another project that I invite you to follow is the RFI Inject, and it concerns the radio frequency interference, a growing problem for synthetic aperture radar. If you look at the reports published by the ground segment of the European Space Agency, you will notice that since 2024, there is an increasing number of radio frequency interference. And these are mainly caused by transmission antennas and how they change over time. So we have specialized algorithms that are capable of removing these radio frequency interference, but since they change characteristics, some of them are not being detected anymore. And you will notice these artifacts in Sentinel-1 data that are here reported in these yellow boxes. So what we did was create the creation of a first dataset of Sentinel-1 level 0 data with artificially created radio frequency interference. This is fully available, it's more or less 400 gigabytes of data. And we also created the corresponding level 1 data in collaboration with a company, Aresis, that was in charge of the processing from level 0 to level 1. There's also a running challenge in our portal, Philab Challenges. It's the Clear SAR challenge, which concerns directly this problem of radio frequency interference detection. I invite you to participate, to read the challenge. There's going to be a track 1, but it's soon going to be released also a track 2. Moving on, this is another problem I wanted to discuss, and that's why I anticipated before, is the problem of focusing synthetic aperture radar. It's a very complex and challenging problem, and it's been addressed in a very different way from literature. This is the standard algorithm, let's say the very well known that you will find in every SAR book. It's the range Doppler algorithm. As you can see from the raw product stepping to these intermediate levels, it's very difficult to understand the real scene. And this is very challenging for an AI model. So in case you want to use directly the raw data on board your satellite, it might be very difficult. And mainly for this reason, we are developing a model that is capable of translating level 0 data to level 1. So this model is based on an architecture which is named structural state space model. And what it does is essentially encodes the phase history of every range beam along the track. What it's doing basically is translating every range line from raw data to a range line in SLC. Not covering every details of this, but I can cover them later if you are more curious about this technique. But what we do in practice, we are capable of focusing the data directly on the satellite, taking one range line as input. And this allows us to do this processing in a very streamlined way. I also call this algorithm the online focusing, because it's the only algorithm that does not employ the full product on your local storage, does not employ FFTs. You can just use a single line and you can focus that line. On the left, you can see the traditional algorithm, the range Doppler. And on the right, you can see the effect of our deep learning-based algorithm for focusing SAR data. Of course, there are some differences, but these are like physical consequence of the way we are treating this data. But still, for some application like vessel detection or flood mapping, still this works and has a very high detailed information. And here are other example of how these algorithms can create level 1 data. Another thing I wanted to give to research and to the scientific community is the IES data. Obtaining IES data is not always simple. Sometimes we buy it from data providers. But in my experience, finding the IES data sampled at seconds, it's very difficult. So what we did was creating this platform for disseminating global IES information. We have a station that receives IES data, and we collected the data from several stations. And we release, thanks to this portal on Hugging Face, all these AIS information sampled at seconds. This allows researchers to build their own data set or also to benchmark their algorithm for any class of sensor that they're trying to develop, either optical or multispectral or radar. Finally, I want to also give you this other tool, which essentially allows you to download almost any kind of satellite imagery. It's a way to access to the Copernicus data space ecosystem. It's a Python package and it's very simple, in my opinion, to use. You just link a few lines of code and you can already start downloading all the data you need from the CDSC. And maybe this I can send it to you. These are some of the data sets that we realized during the years that concern maritime domain awareness, disaster response, and covers a bit the raw data part, but also a bit sometimes higher level data. I can send this offline so you can have a look, but in case you have some questions, I'm very free and open to give you support. And this concludes my presentation.
Thank you very much, Roberto, for a very nice presentation. Any questions from the audience? Armando has a question. Go ahead.
Hello, Roberto. Thanks for the presentation. It's really cool. It's a lot of questions. I think I need a lot of time. I try to find just the most urgent.
Yeah, no,
really cool.
I tried to speed up because it was a lot. I'm sorry if something was a bit confusing.
No. It was all very nice and clear. No, it's cool. When it comes to the first one where you were talking about the trying to detect ships on board, so without doing focusing.
Okay.
You said that they may have this strange shape in the face, but you may struggle maybe if you go for small vessels. Maybe they may be more difficult to do.
Yes.
Have you tried something? Maybe it's a bit computationally more complex, but you've tried something like a type of step approach where you try to look at the Doppler. You see things that bunch off in the Doppler, because the ships will probably have a different Doppler than the sea, and each one will be different. So maybe you can cluster them that way. And then if there is something, you need to process. Have you tried something similar?
No, we did not try, but this is a very valuable suggestion. And in my opinion, what you say, this is true. Like when the vessels are very small, you don't see this very strong pattern in the phase information. But also you have problems when two vessels are close or when they are close to the land.
Yep.
This is an approach
Yeah,
that
yeah.
has its limitation, let's say.
Yes. But in terms of processing time or things you can do in space, are convolution complicated? So FFT and product and IFFT, are these things complicated?
We don't do FFTs for this problem in particular, but the problem with FFT is the length of your arrays. For a strip map product, you have 20,000 elements for a single array. So you can imagine the computational complexity of that problem.
Yeah.
Here we're not employing FFT, but
because you could do quick looks. If you can do just convolutions, then you can get a quick look of the image, and still the small ship will miss, but the big one you will probably see. But yeah, I see the complexity of going there.
I mean, still, if you compare like the traditional processor, it's less computational demanding that using a convolution inherently, because the way the convolution works is always an approximation, and for this kind of problems, you don't want to approximate. So in this case, this works pretty well because you're not applying any kind of processing to your SAR data. You're just analyzing a geometric pattern, if you want, in your data to extract that information. But as soon as you step to the problem of SAR focusing, like here, and you start to resonate, okay, I use an autoencoder, I use a unit, you will find out that you are not so efficient like you think. And that is mainly the reason why we use this other class of algorithm that treat the data in a very, very different way. We're not analyzing the data as like a sort of autoencoder, but we analyze it like a sort of recurrent neural network that has prior knowledge of the phase information from the past experience of the previous range lines. And this is also the reason why you have these outputs that don't match the range Doppler algorithm, because you're using half of the bandwidth, if you think about it. You're not looking back and forth, you only look forward, right? So you have half of the bandwidth and you have an higher PSNR.
Yeah, that was my question on that. So if you look at a line, how do you focus the azimuth if you look at ranges? But you're saying you do look at the next lines, right?
No, you don't. So you say that you have a trade-off. The very cool thing about this, and why I love it so much, is that you are processing one line at a time while you are acquiring. So you are doing a processing at sensor level. So it means that immediately when I am on a vessel, I can tell you that on that line there is a vessel. And I can immediately, let's say, trigger an alert to the coastal guards. Let's say, okay, this is a marine protected area. I found that there is a vessel, it should not be there. You should go there and check. And I can tell you there while I'm on it, not at the end of the acquisition, not after I processed and I'm downloading the product. I'm going to tell you when I'm on that vessel.
So you truly look at a single line, one per
Yes.
time, range.
Yeah, this is the let's say the single line in the raw product, the level 0. Then it goes inside this model, this very, very complicated model with a positional encoding of the range information, because the azimuth filters, let's say, change during near range and far range. And the model has like a sort of inherent memory inside. This is how I see it. A sort of memory bank of the previous range experience. And thanks to that, is capable of focusing that specific line.
Yeah, it must be that indeed, because otherwise you will have range migration. If it's in one line, the next line you will still have it, but it's a bit farther away.
You touched a very important point. No, I am assuming that the synthetic aperture is linear. If you have the problem of curvature, okay, of the range migration, of the range walk effect, in that case, you need to correct for that using information coming from the neighboring, let's say, range bins. But for this problem in particular, because this is the first prototype demonstrator that I'm trying to demonstrate, using strip map from Sentinel-1, I can demonstrate that the curvature induced by the range walk effect is not so big. so that we can assume that we can just use each column as a separate column, each azimuth column, and in that way we just use these algorithms in a separate way.
Could you ask another thing very quick?
Of course, all the question you want.
The RFI things, it is super relevant now with biomass. Have you tried to see a biomass image? 1/2 as some RFI. It's very, very common.
Not yet. But the thing of the
speed band.
Yes, I've been told also for NISA is a problem.
Yeah. Yes, true. Yeah.
I've been in contact with Jan Soldo from Estec, and they have a contract with a Resys. They are trying to solve this problem for I think for Roselle as well.
Yeah, you will yes. But the way that you do it on board is by notch filtering, no, it's more complicated.
Okay. I'm not doing it. So this is the trick now. I just created a data set taking the raw data and injecting the RFI that I artificially create, so I can control how it's created.
Yes.
And we made a challenge in which user is going to use their algorithm to find which is the most effective. So I will use the community in a way to see what works the best for. But of course, notch filtering is one of the traditional algorithms to do RFI.
The problem in biomass is that you have so little bandwidth. If you start chucking things away, you're left with very little. But Sentinel is better. It's just more bandwidth to play with. Yeah. Now this is cool.
I mean, Sentinel-1 tops, in my opinion, is still very little bandwidth, but
yeah. But compared to biomass, is huge.
Maybe. I have not worked yet with biomass, but.
No, but it's cool. The funny thing, these AES things are publicly available.
Yes, platform. You can access to this link. Otherwise, I can send you another link. So what we do is we capture all this information every day and we release it every day. We upload every day a new Parquet file with millions of IS information.
Yeah, so we can go to the historical.
Up to a certain time, let's say when we started acquiring. This is not like a long-term archive. We started last year, I think around August, something like that. Then we had a little problem with our antenna. So the system broke for a month or two, something like that. So we had to physically repair it. But now it's fully operational again.
That's cool. Historical data, normally they ask for good money to have it. So it's good that we can get from there.
Yeah, they cost really a lot. I remember like trying to get some of these sample.seconds. Like I really like it because you don't have to interpolate in your SAR images and they charged me something like 10,000, around 10,000 for that. So yeah, I think this is a very valuable resource for people that work in the maritime domain awareness scenarios, but let me know what you think, if you think that there should be improved something.
Thank you. All very good. Thanks.
Thank you.
Very good. Roberto, I have just one question. Regarding your AI models on board, when you use those AI models for different tasks like vessel detection, I think it's important that to have a lightweight models. I mean, do you think that this is one single model for just one orbit or for your all models? How do you fine-tune just the models to work in all scenarios or different times? Or is it that trained on the images on the ground and then you just deploy it on board? And how was the accuracy in terms of the performance of the AI on board models? If you test it?
I have a very strong opinion on that. Might hurt the scientific community, but to me, it's not like to have a general encoder for an orbit deployment, but you should have a small model tailored for your data distribution and task every time you change data distribution and every time you change task. And that is why I use the neural architecture search, because each topology of your model, so the way the layers are assembled together, it should fit in a way that maximizes the hardware that is available on your satellite, but also the data distribution. Let me clarify. Let's say that you have a specific processor on your satellite. For that specific processor, you might find that certain layers, even 3 of them, are faster and more efficient to run than a single layer that on theory, on mathematical theory, it should be faster. This is because when you challenge the physical world, you have physical memories and pins and placed in a specific way on your processor. It's what is called in literature memory access cost. If you don't take into account the memory access cost, you will pay it later when you deploy your model. So in my opinion, when we think about deploying models for on-orbit execution, I am more keen to spending more computing power on the ground to find the right topology, the right model that fits that problem at the best, than then later paying more power consumption on the orbit. Because when you tailor these models and you shrink it so small, then when you deploy it, they consume very little power. And that stress less your batteries on the orbit, on your satellite, and extends definitely the lifetime of your mission. So in my opinion, it's better to spend some money to find the best model on the ground than later on to deploy a larger model on the on orbit.
Okay, and one more question, maybe that's the last one, because you showed that you have done RFI detection or calibration or SAR focusing. Do you think that it's good to have multitask AI model that doing all these tasks or just doing separately?
Well, in my opinion, it's better to do it separately, but up to a certain level. The direction that I see the world scientific community toward is to one single generalized AI model that can perform everything at the same time. And when I say that, I think about the geospatial foundation models that are trained with these self-supervised approaches to solve any kind of problem later. So my view on this is that it can make sense to have this kind of models that are very generalizable, but only if you can use very few data to train it. If you have enough data.
Yeah, I wouldn't mean to have one general model, to have multi-heads that the one head does SAR focusing and another head does, for example, calibration or RFI detection or whatever in just as a multitask foundation model, not just generalize it. I mean, for example, you showed one model for like SAR focusing and another model for RFI detection. I mean, my question is that it's good to have one big model with different heads. I mean, that does all these tasks in one go.
Okay, to put it simply, my answer is that it's better to have separate models, but it's better to have one single model when you don't have a lot of data to train your models. When you have few samples, it's better to use a generalized encoders that has been trained on self-supervised with a self-supervised policy, because it's faster and easier to train that one on few samples. So let's say that your downstream task that you collected some label data on very few samples. If you don't have a lot of samples, it's easier to use a single encoder with multiple heads and do the downstream fine-tuning. But if you have enough samples, it's better to use a tailored model for your downstream task.
Okay, very good. Thank you. Just one final question. So you showed the result of RFI detection in Sentinel-1. How far we are to get these results on board for Sentinel-1 users just in future? Do you think that we are ready to get such products, AI, on board the results that are already?
Well, in my opinion, we're gonna see this kind of technology, I think, in 10 years. That's my expectation. Okay. Not on Sentinel-1, probably on Sentinel-1 NG.
Okay.
We're still far from deploying this model directly on our satellites. Also because we lack of the scientific validation of an AI model. If you think about it, this new domain of AI on orbit lacks of all these certifications. So when we can say that a model is actually ready to be deployed on an operational scenario, when we can certify that model, if you know what I mean.
Yeah. Thank you very much. Any other questions from the audience? I think, yeah, maybe not. I ask Claudio to conclude the webinar.
Thank you. I hope you enjoyed this presentation. We ran out quite a bit, so I guess that's expressed the interest. So I take it as a compliment. And obviously, we are available offline. You have now the emails of specifically this fellow. I feel welcome to contact them to discuss potential collaboration. You know the options. We already presented them last time. So now it's up to you.
Thanks a lot, Claudio, and all your colleagues for very nice and fruitful presentations. I appreciate all. I will keep in touch and ask others if you have any questions to directly contact Claudio or myself and others via email. Thank you very much all, and have a nice weekend.
Bye-bye.
Thank you very much, everyone. Bye-bye.
Thank you, guys.
Bye-bye.
Bye-bye. Bye-bye.
Ciao.
Bye-bye.